In this last section of light behavior, we're going to look at the calculations that go along with interference. So the first thing we're going to look at is actually a little animation right here. And on this animation, what you're going to see, oh, there we go. Okay. What we're going to see is we have this, it's a silly cartoon version, but this actually really happens with light. This is a famous experiment done by a scientist named Young. It's called Young's double slit experiment. So basically what he did is he took a light source and he shined it at a screen that had slits in it, or a grating maybe would be a better term for it, and then looked to see what happened to the light on a screen that was behind it. So you would expect that if light behaved merely as a particle, if it were to shoot in this direction, most likely it would hit the middle and bounce off and it wouldn't go through at all and you'd see nothing on the other side. Or possibly if it were able to hit one of the slits, it would continue and you'd see one dot. So maybe you thought maybe some of the photons would get through one and some of the other. So you might see two dots, but actually a strange thing happened. Instead, when the light was shot through two slits, thus the double slit experiment, you get an interference pattern. Now this was more confirmation that light behaved the way that diffraction does with water and sound waves and other things. So that light followed Huygens' principle of diffraction. So you can see a couple things on this, is if you change the separation between the slits, as I put the slits further apart, the interference pattern actually becomes more dense, and as the slits come closer together, the interference pattern spreads out. An important thing to note about this is that this looks like these, slits are like a foot apart. In real life, these are very, 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 very small slits. We'll actually replicate this experiment in class, and the slits are so small and so close together that you have to really look closely to even tell that there's two of them. So these are very small space slits, and you have a large distance between the light and the screen. So when we talk about the math that goes with interference, we're going to look at that interference pattern. So imagine we're looking at that same animation, but we're looking from above. So the light source would be at the bottom by the slits. And then where we saw dark and light spots, you would see the bright spots would be constructive interference, and the dark spots in between would be these dotted lines would be destructive interference. So the thing causing this interference pattern is the same interference picture that we looked at before. So there's two different, basically becomes point sources for the light as it goes through the two holes, and those point sources, as they propagate the light, as the light continues to spread out, is going to form an interference pattern. So that's what we're seeing here. And we're going to take a look at, Young is famous for the math that goes along with this. We're going to look at a little bit of math that can allow you to find out a few things about the light you're using. We'll actually use this in lab to try to determine the wavelength of laser light, of the little red lasers that we use in class. So basically here's how he did it. We're going to zoom in then on this interference pattern, and then this would be the screen that the light is being shined on, and as I go in between the two slits, I'm going to draw a line through the zero order line. So this is my first line and this is my first variable. So I'm going to have four variables out of this. So the distance from the S1 and S2, this would be the diffraction grating or the double slit. The distance from the slits to the screen is going to be called L. Okay? And then we're going to take the distance from the center dot, from the zero order line, which in this case is going to look more like a dot than a vertical line. The distance from that to the first dot to the either left or right, we're going to do it to the left, but to either side, that variable would be x. So that's the distance from the zero order line to the first antinodal line, or they call them a fringe oftentimes in this section. Okay, so we're going to complete the triangle, so that's what this last line is, just to make a nice triangle. And we're going to do some right triangle stuff here. So we're going to make a different triangle, and we're going to compare the two. So I'm going to start with a line between S1 and S2. This is the variable d. That's a nice simple one. Distance between the slits is d. Again, this is very much not to scale. D would be very, 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 very small, but if I did it to scale, it would be very difficult to actually see much of anything. So this is very much not to scale. So D is the distance between the slits, and again I'm going to make a triangle to the first fringe. So there's a reference triangle, and I'm going to make one last triangle. So we have D, the last one. We're going to use a portion of this larger orange triangle, and we're going to look at the distance to the first wave crest. So the distance from S2 to the crest, that would be the wavelength. So if I label that as the wavelength, whoops, and then complete the triangle, I have a third triangle down here. So it's looking at these two large, or the two main triangles we're looking at is the green one and then the shaded one down below. And excuse my PowerPoint, it doesn't exactly perfectly match up, but you can kind of see which triangles that I'm talking about. And these are basically, well, the green one is obviously a right triangle. The orange one is close enough to a right triangle. They use what's called the small angle approximation, which is the science way of saying close enough in order to justify that. So we're going to use then the two angles inside these triangles. We're going to use this one and this one. And the important thing to know is that these are similar triangles, and being similar triangles, these two thetas are the same. So we're going to get two equations then, one for each triangle, each of them involving theta. So the trick is that theta in both of these equations are the same. So for the green triangle, I'm going to use, well, I put both of them up there, but for the green triangle I'm going to use tangent. So tangent is going to be opposite over adjacent, so that's why tan of theta is x over L. And then for the bottom one, I'm going to be using the sine of theta is going to be lambda over d. So those are my two interference equations that we'll use. The trick again being that the thetas are the same. So oftentimes these problems will ask you to solve for theta in one equation and then use it to solve for a variable in the second equation. Sometimes it's straightforward, you only have to use one, but more often they make you use both of them. Okay, so here again, this is just another sketch, and this is the one that you should have on your notes packet. I thought it was a little more clear, and yet I wanted to show you the whole pattern with the previous one. So here we have our two matching triangles. So that might look a little better with my triangles than the last one did if you're trying to make sense of my trig. So it's the same idea. By the way, this is a really abstract section, and to me it's not worth having you guys memorize where the variables are in the diagram. So I'll give you this exact same diagram on the test, and you can use that then to know, like, oh, if I'm solving for x, what on earth am I solving for? You can look at the picture and look at that there. So again, there's my two equations, so those are the ones that we'll use here. I wrote out the definitions for each of the variables, and I won't read them here. If you want to write them down, you can pause the video. Alright, so we've got a couple examples for you. The first one, here I'm using sound waves, and again, we're mostly studying light in this chapter, but interference is a behavior of all light, so occasionally you'll see examples for other things, in this case sound. So in this one, we have sound waves pass through double slits separated by 22 centimeters. For light, it would be a much smaller distance, but for sound that's reasonable. The first maximum, so the first constructive spot, is 14 degrees from the center. What's the frequency of the waves? So they gave you D, that was nice, they gave you theta, and they're looking for frequency. Now because we know the speed of sound, oh, well, I guess I didn't do that first. Okay, we will use the speed of sound here in a second, but we can say sine of theta then is lambda over d, and they gave us the variables theta and d, so we can go ahead and solve for lambda. So we know the wavelength, but they asked us for the frequency. Now we know this, we've been doing this for a while now, because we know v equals f lambda, which here is rearranged for frequency, we can go ahead and solve then for the frequency. Here they use 340 meters per second. If you use 340 or 345, if it's not given, either one will give you a very close answer, so either way is fine there. So this would be a simple example of how you use an interference problem. So they might ask you for just one equation. I believe I gave you on the second one that's going to use two. So here we're going to talk lastly about diffraction gratings. Young's double slit experiment used just something with two slits in it, but you can have a piece of plastic, and we'll look at these in class, that have tons and tons and tons and tons of little etches in the material. Usually they use plastic, you could use glass or something else. And so basically it acts like a double slit where it forms an interference pattern, except instead of having the light go through one tiny little spot, the light can really go anywhere through the grating, and what happens is then the light is going to be split into its component colors. So they use diffraction gratings, or the idea of this, to be able to find out what elements are in light, for one thing. So we'll take a look at these in class and look at a couple different things with them. So there's my definition for diffraction grating. So the thing that you need to know, the first thing you need to know is that this behaves just like a double slit. So but there's one other thing that you need to know. When you're given a diffraction grating, they have a rating. So the rating is usually something like the ones that I'll give you in class to look at are rated at the 13,400 lines per inch. So I told you it's a lot of lines in 1 inch. I mean, it's really, you can't really see the lines. You can feel that the material is rough. But the lines per inch isn't a variable that we use. Instead, what we need is the distance between two lines. So if we have lines per distance and we want distance per inch, what you need to do then is invert the value for the rating, and that will give you D. So important things to know about diffraction gratings. One is that it behaves the same way as a double slit, and two, that you have to invert D, or I'm sorry, invert the rating, the lines per inch or lines per centimeter, in order to get D. And also with this here, I gave you centimeters and inch. You do have to convert that into the unit that match the other distance units in the equation, which could be centimeters or inches, but they all have to be the same distance unit. It's usually easiest if it makes you nervous, convert everything into meters, and then you won't have to worry about the conversion problem anymore. So here's a diffraction grating example. So here a diffraction grating with 13,400 lines per inch. They give you the distance from the tube. In this case, it's neon gas. So how far to the side of the tube will you see a violet band of 442.5 nm? Remember, nm is nanometers. Okay, this is something that you've probably done in chemistry when you see the gas tubes and you look at them through a diffraction grating and you can see the lines split up. You see different little colors at different distances. You may or may not remember doing that, but that's a common chemistry thing to do. So things that they told us D. When they give you the lines per inch, they're actually giving you the variable D. So you flip that over and you get the distance for diffraction grating here in inches, so you want to convert that. In this case, I left it in centimeters. You could do it in meters if you would prefer. Okay. The distance to the tube, that's L. That's always going to be the biggest distance in the problem. Lambda was given. You can't use it in nanometers, of course. I went ahead and put it into centimeters so that my D and my lambda were in the same distance unit. Again, you could do that in meters if that bothers you, if you have trouble with the conversions at all. And you are always welcome to use your calculator to do those conversions. So in this case, they say, how far to the side of the tube do you see the violet band? What they're asking you for is X. So here's how we do this. First, we're going to go ahead and find what that angle is. So my 0.2334, that's the sine of theta. I'm going to use that to find the angle. 13, that's actually a fairly big angle in these kind of problems. Usually the angle is very small. If you get an angle of like 70 degrees, you've probably made a mistake. So you're looking for very small angles here. So now that you know the angle, we're going to pop it into the other equation. Here it's rearranged for x, since that's what we're solving for. And so we're going to do the tan of that angle times L is going to give us the distance here in centimeters. So I made that look really simple, but usually I have kids struggle with this. The whole idea of these kind of problems is to find theta and then use theta in the other equation, because they don't usually give you enough information to just do it in one. So that's how interference problems work. And I do have a cool video for you on the double slit one. I'm going to post that on YouTube so you can watch that separately, but your homework then is to work on the interference problems. Actually, we'll work on that in class, so your homework was just to finish these notes. Cool stuff? Good. All right. See ya.